Okay, hello. I'm now reporting you the progress of the matrices 2, and also first how to multiply matrices with the scalar value. Okay, here I have, in fact there isn't this one yet. Let's make a new one. Okay, so when we have a, let's say, value scalar c, and we multiply it with a matrix D, E, F, and G, is the same that as with vectors we multiply C times D, and this element is C times E, and this element is C times F, and this element is C times G, and so we have a next matrix. Okay, how to identify which matrix multiplication operation are valid? The validation of matrices, don't say. The amount of the A's column have to be with same as B's row. So that's why A times B isn't same that B times A. So there must not be as with the numbers, because if it can be, but in that time to have to be square matrices. So amount of A columns isn't same as amount of B rows. It's an invalid. Okay, let's move on. How to multiply matrices with another matrices. Okay, here we have A and B, so let's do A times B. And here we have an example. For example, 1, 0, 2, 1, 4, 0, 2, 1 matrices are multiplied with this kind of way, so that yellow number becomes from that row multiplies with that row by using this kind of formula. That, let's take a little one, this one goes to here, plus this times over there, and this times over there, and this times with this one, and the second one becomes a same way by adding multiply with each other and adding them together. And so we have this kind of, so as we see, this is 4, not exactly, this is 2 times 4 matrices, and this is 4 by 3 matrices. So this is this matrix, which is a result, is times 3 matrices. Okay, then how to multiply matrices and vectors. Vectors is as just one row. If it's a column vector, it's a one row matrix. So in this time we find out that this matrices and this vector cannot be. This is an invalid. Because the columns and rows are not the same. But in this time we find out that this one is same. The amount of columns is the same that amount of rows, so we can do the multiplication with each other, and so we have 2 times 1 over here, and 1 times 0 over here, 4 times 3 over here, 0 times -1 is over here, and the result of that is a 10, and then with a second column, a second row with this column becomes from this one and this one or this, and 1 times 0 becomes this, and 6 times 2 becomes this, and then the last one is this one over this, it becomes this, and the result is 16. And with the same time with this this row and this column, which is now a vector, and so on, we have this kind of vector result. Okay, then move on. How to calculate determinant of a matrix. The determinant of a matrix is only possible with square matrices, and that's why we can find determination of determinant of 3 by 3 matrices by this version or by this version, which is much easier. But this doesn't work. This works only with 3 by 3 matrices. But this is the version to do with every n to n by n matrices. But it's more complicated. But anyway, we take, and as you see, these are the same. These are the same formula in different representation, because this BC over there minus a times EG, which is over here, and so on. Okay, then how this comes is we take A first, and then we take this minor for this one, because we how do you say, delete these rows and these columns which the A hold, and so on. We move on with this one. We erase these rows and columns, and so on. We find GE, IGF matrix which determinant is the here is the determinant of this one, which is another element of this multiplication, and so forth. But there is a minus over there. Okay, let's move on. And the determinant of the bigger square matrices is much complicated by this formula, and always determinants is the number, not any matrix, not vector, or it's a number. And over here I explained that if K, L, M, N, O, and P, these ones are 0, or the upper one is a 0, then these elements times each other, the product of these elements is the determinant. And how to change any matrices in this kind of to this upper triangle, it is possible by using elementary row operations. I don't explain it over here. And here is a simple example how to determinant of A, and this is an A matrix. So we take these ones over here, 2, 0, and 0, because there's a 0, and then here comes, there's a 0, and then there is 0, and then there's minus 9 times 7 is 63, and the result is minus 61. And which I didn't explain was that in this we duplicate these two columns over behind here after the matrix, so we have this kind of, this could be also rolling back here, and this one can be rolling back here, but it is much easier to come back to minuses. Okay, let's move on. How to determine if matrix is invertible? Okay, matrix is invertible if the determinant isn't 0, and it is because by this formula, if this one is a 0, its determinant is a 0, this is unavailable. Undefined is the correct word. Okay, here we have a matrix A, and how we do this is we take a matrix of minors first. So here in this case, it's a determinant of these elements matrices, and this one is an element of these ones, and so on, so forth. And by this we have a matrix of